Welcome to the Embedded Analytics Functional Debug demonstration. My name is Andy Gothard, Senior Marketing Programs Manager in the Tessent Group within Mentor, a Siemens business. Later, you'll hear from Hanan Moller, who leads our Applications Engineering team, and will talk you through the demo itself. Before we start with the demo, I wanted to give you just a bit of background on Tessent Embedded Analytics. What we provide is a hardware-based monitoring and analytics solution for SoCs. We embed monitoring and analytics IP within the SoC itself. This brings three main benefits. First, in lab, we accelerate silicon bring-up, debug and optimization. Second, in post-deployment optimization, performance tracking and tuning, etc. Finally, our monitoring infrastructure can be used to implement safety and security features, monitoring for anomalous behavior of any type. The solution includes hardware monitors to acquire behavioral data from the chip, software tools to configure and program the monitors, and the data we collect is then analyzed with the aim of distilling it into actionable information. Applications for our technology include storage controllers and compute servers, and machine learning SoCs with hundreds or even thousands of CPU cores. Now, I'll just do a quick run through of the embedded analytics hardware architecture and some of the IPs that we provide, all of which are delivered as synthesizable Verilog RTL. The green blocks here represent the main system of your SoC. You might have several processors, accelerators, and many other types of IP. There'll certainly be some kind of interconnect or NOC. Some of the IP will be purchased from commercial providers. Other IP you'll have developed in-house. Now, there are four families of IP in the embedded analytics portfolio. The first is what we call our analytic modules. As the name suggests, these are smart monitors that gather and pre-process data from the various function blocks on the chip. For configuration, data collection and cross-triggering, we have a flexible and scalable message fabric connecting all of our IPs together. And obviously, the IPs also need to interact with software. That might be analytics software running on the main system, or you might use a dedicated analysis subsystem directly connected to the embedded analytics message fabric. Or again, you might want to go off chip, for instance to an IDE, as we'll see in a few minutes. So we have communicators that cater for different technologies, different speeds, starting at traditional debug over JTAG, or USB 2 at 480 megabits per second, or the EBC for USB 3 type speeds, and so on. The last family of IPs are active managers, which provide solutions for security and functional safety. And finally, it's worth mentioning that we include a system of message locks, which allow you to lock down the embedded analytics infrastructure and protect the data you're collecting. Now, just to dig a little bit deeper and give you a feel for what we mean by smart monitoring, the bus monitor or NOC monitor shown on the far left is a good example. It's protocol and transaction aware, so it can look for specific types of transactions on the interface, whether that might be address-based or ID-based. It's smart enough to take performance measurements of those transactions, for example measuring bandwidth, minimum latencies, or maximum latencies in timed windows, and so on. So it gives you a lot of information about what patterns of accesses are happening on the interface. The analytics modules also include processor-specific IPs. The Processor Analytic Module, or PAM, provides an interface to a CPU's debug module for the purposes of debug and run control, and the trace encoder for program trace. The demonstration we're showing runs on an FPGA platform. It's a Xilinx Zinc-based system. It has a hardwired ARM processor, and we've instantiated two Andes RISC-V cores in the FPGA fabric. We're running some simple fractal generation and display code on each core to give us a visual indication of what the cores are doing at any one time. Each core is supported by a collection of embedded analytics IP instances, and we have our ultra-developed IDE connected to the system via a USB 2 link. The first part of the demo shows run control on the RISC-V processors. We can insert breakpoints, single step each core separately, and so on. And that allows us to take a detailed look at code execution, various variables, CPU registers, and so on. The IPs we are using are the JPAM for run control and the USB communicator for communicating the information to and from the IDE. So now I'm going to hand you over to Hanan to show you the demo.
In this part of the demo, we will see how you can use AlterDevelop 2 to control and debug a multi-core system. In this system in here, as you've seen in the slides earlier, we are running two RISC-V cores, in this particular case, Andes cores. Here is one of them, and here's the other. And there's also an ARM core that can be used, but we're not going to use it in that part of the demo. Each of the cores is running a program, in this case an identical program, but they're running slightly offset from each other, as you can see down at the video feed below. Some of the things that we can do in here for normal debug operations, we can suspend both cores. You can see that the execution had stopped, and we can see where the state of the different cores. We can now go and let's say we will choose to look at core 0. We can see the disassembled code of where it's at. We can observe source level variables, CPU core registers, change them if need be, and so on. We can, let's go back to this view over here. We can now perform a single step. So in this particular case, we're single stepping at a source code statement level. So you can see that we step instruction by instruction. Am I at the right core? Right here. We can put it into single step at an instruction level if need be. So you will see on the right hand side how the program counter advances from one instruction to the next. We can also set up breakpoints, enable some breakpoints. So for example, let's put a breakpoint right at this point in here. And resume operation. We hit the breakpoint over here. We can get the other core to just continue running by selecting it. So that particular core is has hit each breakpoint. We're using the same source code in here, so the breakpoints are being shared in this particular case. So I will just ignore this core in here, and we will focus on core 0 for the rest of the demonstration. So once we've hit the breakpoint, we can then go and resume execution to run, let's say, another iteration of whatever the program is doing, and single step a little bit more if we need to. We're still in instruction stepping, so we'll turn that off and go at the statement level.
The next part of the demo is RISC-V processor trace. Now, as you may know, our embedded analytics technology became part of Mentor when we acquired a UK-based scale-up business called Ultrasoc. Ultrasoc was active over a number of years within the RISC-V community to define a standard for processor trace. That specification is now ratified, and our trace encoder is compliant with it. We'll see how we configure the encoder, capture a few traces, and then look at them to see the capabilities that they give us. The embedded analytics IPs that are interacting in this demo are predominantly the trace encoders. For simplicity, we'll just look at the trace from one of the cores. And what we're going to see is that this is a very powerful tool in terms of debug, performance analysis, code coverage, and so on.
In the previous part of the demo, we have seen how to achieve run control operations using AutoDevelop 2. In this part, we will take a look at some of the instruction trace capabilities that are provided by the Embedded Analytics Trace Encoder IP and the AutoDevelop software. So what we will do in here, we will upload two, what we call two instruction trace tasks, and those can be, so the instruction trace can be set up to filter start and stop tracing on particular address ranges and so on. We will take a look at two different examples in here. In the first example, we will trace a small part of the code, and in order to do that, we configure the trace encoder to start tracing when crossing this particular address and stop tracing when crossing this particular address. Let's see where we are in the code. So before we do that, we need to enable the trace. So we've selected the addresses, enabling trace, loading the configuration. We get feedback from the trace unit that the trace had been enabled over here. Now let's just look at the code. We want to make sure that for the purpose of this demo in here, that we enable this breakpoint in here, just so that we don't get overwhelmed with a lot of trace information and can really look at the details of the trace output. So once this is in place, I will now let the code go on running. So we've hit the breakpoint in here. The trace address range I've requested is the one being covered by in this range. So we've just at the start of this range, and now when I resume, we ran one iteration and then we got some trace information coming out in here. Let's just look at it a bit more. The information that we're getting in here is showing the trace packets as they come out of the trace encoder. And one thing you will notice in here are those full delta bitmaps, which indicate whether branch instructions in the code were taken or not taken. Now we can take this information and show the disassembly and get the reconstruction of what the code was doing. So we can see that it started with this switch statement, and then based on the specific values that it was looking at the moment, at the time of execution, this particular set of branches was taken or not taken, as was the case. So by looking through that, you can get a clear understanding of what was the sequence of instructions that was executed. We are not limited to necessarily small chunks of code that to trace. Let's look at a slightly bigger trace example. I will firstly disable this particular trace function here. So we disable that trace, and here trace was turned off, and I will enable a trace which is going to work in a slightly different mode and a wider address range, which matches a region I will show in just a second. We apply the configuration, and this particular range is looking at this piece of code in here, which will iterate I believe 10 times over this code. So if we then, okay, so now we're at the breakpoint at the beginning of the region of interest. You can see that quite a lot of trace has been captured in here. So if we now open the disassembly for that, we probably want to skip the first few parts in there because this is the output from the previous run. But you can see that the entire thread of execution is being disassembled, and you can then follow the thread of execution and fully understand the behavior of your program.
Thanks for watching the Embedded Analytics functional debug demo. If you'd like any more information, please feel free to contact me or Hanan. Our details are on the screen now.